Hey everybody, welcome back to chemistry, and we are continuing on with chapter 7 in the gas laws. And so in this presentation I want to cover some more gas laws and some other information to help you solve problems. And so the gas laws I want to cover are the combined gas law, which is talked about in section 7.4 in your book. Also I want to next cover Avogadro's law, which is in section 7.5 and 7.9. The ideal gas law, which is in section 7.6. Then there is a way that you can take the ideal gas law and identify other gas laws from it. I want to explain to you how to do that. That's also in section 7.6. And then finally, we'll talk about how the ideal gas law can be manipulated to help you find information about gas density or its molar volume. And this is in 7.8 of your book. Okay, so here we go. So let's talk a little bit about the combined gas law. So I have it there on the screen, and so the thing that you'll notice is kind of similar to previous gas laws, but a little different. So the way it's similar to previous gas laws is what we used to do is we would have a gas at some kind of initial condition, say we'll call it condition 1, and then we were relating to it the gas at new conditions, we'll say condition 2. So that is still there when we see this combined gas law. But here in the combined gas law, instead of seeing two variables being related to one another, now we're seeing three variables. And so those three variables are pressure, volume, and temperature of a gas. So we can relate those three variables at a new condition from the gas at the original condition, as long as we understand that that gas is not changing its number of moles as you're going from that original condition, condition 1, to the new conditions, condition 2. So one thing to notice about this law is basically it's a fusion of some of the earlier laws we were looking at that had two variables in them. So one thing you can see in there in that law is that there is Boyle's law in there, which is P1 V1 equals P2 V2. Superimposed on that is Charles' law, which is V1 over T1 equals V2 over T2. And then Adamanton's law, which is P1 over T1 is equal to P2 over T2. So when they're all fused together, it gives you the combined gas law. And so one thing you'll have to do when using this gas law is if you have a temperature in something other than Kelvin, you will have to convert it to Kelvin. So most of the time in these problems you'll have a temperature in Celsius, and so if that is the case, then just add 273.15 degrees to get it into Kelvin. Probably the best thing to do is for me to try a problem like this on the board, and I'll give you some tips to solving this. Okay, so we have a gas that occupies 10 liters at 240 degrees Celsius under a pressure of 80 kilopascals. At what temperature will the gas occupy when it's at 20 liters if the pressure is increased to 107 kilopascals? And so looking at this problem, what we can see is that we have three pieces of information, three properties, which are the volume, the temperature, and the pressure of the gas. And so let's see if we can define some initial conditions and then see what we need to solve for in the new conditions. So the volume initially is 10.0 liters for this gas. The temperature is 240 degrees Celsius, and so I'll have to convert that to Kelvin in just a second. The pressure is 80.0 kilopascals. Okay, so let's see how we can define the variables in the new conditions that we're going to bring this gas to. It says at what temperature. So it looks like we're trying to find T2. So that is the unknown in this problem. Let's see, we have a new pressure, P2, which is 107 kilopascals. And then we have a new volume, V2, which is 20.0 liters. Okay, so we're trying to find T2. So I think what I'm first going to do before I derive the appropriate equation that we can plug in numbers to is just first, let's just take this initial temperature at Celsius and convert it to Kelvin, sort of like as I was doing it before. So what you do is you add 273.15, and kind of like I pointed out before, we'll get a calculator answer, which is 240 plus 273.15. So the calculator answer I get is 513.15. But I think at this point, what I want to do is solve this problem in the way that the book does it. And what the book does is when you have a temperature, the first thing you do is get that into the correct number of significant figures, and then once that's done, plug it into the equation and then solve. So we have 240, and there's a decimal here, so the uncertain digit in 240 here is in the ones place, so this has 3 significant figures. The uncertain digit here in 273.15 is in the hundredth place, and so there are 5 significant figures here. And so again, the calculator answer will be 513.15, but you might recall the rules for adding numbers for significant figures. And so here, the number we should get should be rounded to 513 with its uncertain digit in the ones place. Okay, so this will be in Kelvin, so I'll put a K here. Okay, so the next step is to go ahead and solve this equation for T2. So let's see if I can do that. So it's going to be P1 V1 over T1 is equal to P2 V2 over T2. So this can be a little tricky deriving these equations for the variable you want to solve for, but what I'm going to do is I'm going to take T2, which is the denominator here on this side of the equal sign. If I want it in the numerator, I have to put it on the other side of the equal sign, so it goes up here like this. And so what we can do is write that out, see what we got now. So we have T2 P1 V1 over T1 is equal to P2 V2. And so the next step is we got to move out the other variables so that T2 is by itself. And so we're going to move P1 V1 from this side of the equal sign, and it will go into the denominator. And it goes to the other side of the equal sign. And T1 here, we have to move out as well, and it goes to the other side of the equal sign. It will go in the numerator like that. And so what I get is T2 is equal to P2 V2 T1 over P1 V1. So I think that's correct. Okay, so let me just go ahead and plug in some numbers and just confirm that the units cancel as expected. So P2 is 107 kilopascals, and V2 is 20.0 liters. And we also have T1, which is here. It's going to be 513 Kelvin. And then over P1, which is 80.0 kilopascals. And then we have, it looks like V1, which is 10.0 liters. So let me see what number I get here when I get this. And so I get 107 times 20 times 513 divided by 80 divided by 10. So the number I get on my calculator is 1372.275. The book again suggests that at this point, after you plug the numbers into the equation, you get a number from the equation. You should round this to the correct number of significant figures at this point. So it looks like, if you check carefully, this number needs to be rounded to 3 significant figures. So here are 3 here. Here's the uncertain digit. We'll look to the right of that. It's below 5, so we do not round up. So what I get is 1370, with this 7 being the uncertain digit. This 0 is not significant. And so remember, this is in Kelvin. So the final step is, I think the problem is asking, well, what temperature it should be. Now, it doesn't say it has to be in Celsius, but let's just calculate into Celsius. So it's minus 273.15, and let's see what we get. So I get 1370 minus 273.15, and so I get 1096.85 on my calculator. But again, we have a significant figure furthest to the left here, and this number here compared to this, uncertain digit here, and compared to this uncertain digit here. And so we have to round such that the answer has an uncertain digit here in the tens place. And so we look to the number next to it, and it's above a 5, so we round up. So this rounds up to a 0, and this next digit becomes 1. So I get 1, 1, 0, 0 degrees Celsius, with this 0 being the uncertain digit. So this has 3 significant figures. So if you wanted to, you could write this as 1.10 times 10 to the 123 degrees Celsius. And I think that's the answer I got on the screen. It is. Okay, so we will move on. Okay, so the next problem I'm just going to point out, I'm not going to solve it, but I encourage you to try this problem on your own. And so you use the combined gas law to solve this problem, which is P1V1 over T1 equals P2V2 over T2. So I encourage you to stop the video for a moment and just try that on your own. Okay, so now we're getting into a new law. And so the new law is called Avogadro's law. It's actually pretty easy to understand, and the reason is because we do this quite a bit in our lives. We have seen examples of Avogadro's law by blowing up a balloon. So imagine that you have a balloon that's just out of the package and it's relatively deflated. Now you know that balloon will have a little bit of air inside of it. That air in that deflated balloon causes the balloon to have a certain size, and so it has a certain volume. Now, you know, if you blow up the balloon, you're basically taking the amount of air that is inside there, which is a certain number of moles, and you're just adding more moles to it. When the moles of air in that balloon increase, then the volume also increases. And so this will happen as long as the temperature is kept constant and the pressure remains constant. And so this is sort of basically Avogadro's rule, is that when you have some kind of flexible container that can hold a gas, if you increase the number of molecules or the number of moles in that container, you're going to have to increase the volume of that container as long as you keep temperature and pressure of the gas constant. So in a sense, what you can sort of see is that as the number of moles of the gas increases, the volume of the gas increases. And so what that says is that the number of moles is directly proportional to the volume of the gas. And so what we can do is we can write that in a pretty simple equation, that V is proportional to N. Now, what you might remember is if you wanted to, you can turn that equation into an equality as long as you add some kind of numerical constant. So if V is proportional to N, you can also write V is equal to a constant K times N. And then if you wanted to, you could solve for the constant K. If you wanted to, you can sort of derive an equation from that. So that'll be V1 over N1 is equal to V2 over N2. And again, this only really applies if the pressure and the temperature are constant between these two conditions of 1 and 2. So again, this is Avogadro's law, that if the number of moles of a gas increases, that the volume increases. I kind of just talked about this a moment ago, the explanation as to why there is Avogadro's law. And again, as you know, that when you increase the number of molecules or moles of a gas in a container, its volume must proportionally increase if the pressure and temperature stay the same. So let's go ahead and try a problem using this relationship. And it says, let's say you have a large balloon with 0.35 moles of gas that has a volume of 8.56 liters at 25 degrees Celsius and 1 atmosphere pressure. If you were to add 1.0 mole of gas to this and the temperature and the pressure remain the same, what is the new volume? So let's go ahead and see if we can solve this problem here. So let me just write out what the initial conditions are. So here we're given an initial number of moles of gas, which is 0.35 mole. And we're also given an initial volume. V1 is equal to 8.56 liters. Now, just a note, we're also given a temperature and a pressure. So let me go ahead and write this here for the moment. So the temperature is 25 degrees C, and the pressure is at 1 atmosphere. Okay, this says, if you were to add 1 mole of gas and the temperature and the pressure remain the same, what is the new volume? So we have new conditions where we're adding a mole to the gas that we already have 0.35 moles of. So N2, after you add that moles to the original number of moles that is there, we should have 1.35 moles of gas for N2. So what we're trying to do is find the new volume that this gas occupies now after it receives another mole of gas. But the temperature and the pressure in these new conditions is the same as it was in the original conditions. And so if that's the case, we don't have to really worry about that in the problem. So we can just erase that. And so if we know a relationship between moles and volume, we can figure out what the answer to the problem is. And that relationship is Avogadro's law. So we again know that the moles of a gas at initial condition divided by the volume of the gas at that initial condition is going to be equal to the moles of the gas at the final condition divided by the volume at the final condition. And so what you can do is solve this equation for V2. To do that, I'm going to move V2 to the other side of the equal sign here. And so I have V2 is equal to N1 over V1 is equal to N2. And so I need to get V2 by itself. And so to do that, I have to move N1 and V1 to the other side of the equal sign. So V1 in the denominator here goes in the numerator. N1 in the numerator here goes in the denominator. And so I get V2 is equal to N2 times V1 over N1. I think that's probably correct. What we can do is go ahead and plug in numbers. And so V2 is equal to N2, which is 1.35 mole, times V1, which is 8.56 liters, over, and it looks like N1, which is 0.35 mole. So what I'm kind of hoping we'll see is that you can sort of look qualitatively at this problem, that if we're adding moles of gas to the gas that's already there, we would expect the volume to increase. So let's just hope that we get out an answer that is larger than the original volume of 8.56 liters. So let's see, it's 1.35 times 8.56 divided by 0.35, and I get 33 liters. So yay! So that is consistent with what we would expect, that when you increase the moles of the gas, holding the pressure and temperature constant, that we would expect the volume to increase, and that's what happens. So that appears to be the correct answer. So we will move on. Another thing you sort of need to understand is you're going to see problems where you may have to take a gas at initial conditions and then figure out what a property of the gas is at something called standard conditions. And so standard conditions are a particular pressure and a particular temperature. And so at standard conditions, the pressure of the gas must be average atmospheric pressure, which is 1.0 atmosphere, which is 760 millimeters of mercury. And the standard temperature would be 0 degrees Celsius, which is 273.15 degrees Kelvin. Now, another thing that's kind of useful to know is you should understand what volume any gas occupies if you have 1 mole of it at these standard conditions, meaning you have 1 atmosphere pressure and 0 degrees Celsius. It's always the same volume no matter what gas you have. At standard temperature and pressure, 1 mole of any kind of gas, it could be oxygen, nitrogen, a mixture of gases, it doesn't matter. 1 mole of any gas occupies 22.414 liters of space. Now again to note, 1 mole will occupy that particular volume only at standard temperature and pressure. So for example, let's say you were to increase the temperature of that gas. And so 1 mole would occupy 22.414 liters of space at 0 degrees Celsius. But you remember from Charles' law that if you increase the temperature, you're going to increase the volume. So for example, if you were to double the temperature in Kelvin, you would double the volume. And so that 1 mole of gas would no longer be 22.414 liters. It would be a much greater volume. So again, this number, 22.414 liters of volume, only applies for 1 mole of gas when it's at its standard conditions of pressure and temperature. Okay, so here's kind of an interesting application of that to Avogadro's law and to solving problems. So let me just go over an example here. So I want you to note here I have an equation for the formation of ammonia. And I want you to notice that all of the molecules, whether they be reactants or products, are in the form of a gas. Now, you already know how to interpret the coefficients of that equation, and so that you can see that 3 moles of hydrogen will react with 1 mole of nitrogen, gives you 2 moles of ammonia. Now, again, just note that all these molecules are gases. And so if we wanted to, we could figure out, knowing what the molar volume of the gas is at standard temperature and pressure, we can take those moles of gas and multiplying by the molar volume of 22.414 liters per mole, calculate how much volume these moles of gas would occupy. And so I'm doing that there in this equation, that 3 moles of hydrogen times 22.4 liters per mole is the molar volume. What you can see is that when you do that multiplication, for example, of hydrogen, you get 67.2 liters. When you do that for nitrogen, you only have 1 mole there in that equation. You multiply by 22.4 liters per mole, you get 22.4 liters. And so for ammonia, you have 2 moles there. You multiply that by 22.4, you get 44.8. But what you might notice is that all these numbers reduce to the original mole ratio. So when you see an equation and all the molecules are gases and you see the coefficients in front, not only do those coefficients refer to moles, but they also refer to volumes. So if 3 moles of hydrogen reacts with 1 mole of nitrogen to give you 2 moles of ammonia, you can also say that 3 volumes of hydrogen reacts with 1 volume of nitrogen to give you 2 volumes of ammonia. An example of a volume here would be liters. And so you could say 3 liters reacts with 1 liter to give you 2 liters, or if you wanted to, you could use different units. It could be 3 milliliters reacts with 1 milliliter to give you 2 milliliters. So just to note, if you have an equation and you have molecules that are gases, the mole ratios are also volume ratios. And usually people think of that in terms of liters, although you don't have to. So let me just give you an example of how to use that knowledge to solve a problem. It says, according to the reaction equation, and again, it's the one we just were looking at, how many liters of ammonia would be produced when 5.6 liters of hydrogen reacts with an excess of nitrogen? Here we have 5.6 liters of hydrogen, and from that equation, what we want to do is figure out how many liters of ammonia are produced. Well, a simple way to solve that problem is to recognize that when you see that mole ratio between hydrogen and ammonia, which is 3:2, that is also a volume ratio or a liter ratio. So we can also say that 3 liters of hydrogen produces 2 liters of ammonia. And so you can use that ratio to set up a fraction there to help you solve the problem. And so what I've done here is I've just set up the fraction of 2 liters of ammonia to 3 liters of hydrogen, and then I flipped it in such a way that the liters of hydrogen cancels out, and so we get an answer in liters of ammonia. So that liters of ammonia, 3.7, is what you would get from 5.6 liters of hydrogen. Okay, so let's go ahead and solve a few problems using this relationship that can be very helpful. The problem we have here now is calculate the volume in liters occupied by 7.40 grams of ammonia at STP. Okay, here what we have is we have 7.40 grams of ammonia. And so what I want to do is I want to get this into, it looks like into liters of ammonia. So eventually we want to get this into liters of ammonia. So how will we solve this problem? So let me kind of write this out down here. Here we have grams of ammonia. And so what you can probably imagine is whenever you have grams of a molecule, you probably just want to immediately convert it to moles molecule. So grams of ammonia can be taken to moles of ammonia. But in the end, we want liters of ammonia. We don't have so much an equation here, but what we can do to solve this particular problem is we can convert moles of ammonia to liters of ammonia pretty easily because we're at standard temperature and pressure. So remember, when we're at standard temperature and pressure, that 1 mole of any gas occupies 22.414 liters of space. And so we can easily convert moles of ammonia to liters of ammonia knowing that. So grams to mole is just the molar mass, and then moles to liters of ammonia is molar volume, which is, again, 1 mole of any gas occupies 22.414 liters of volume. Okay, so what we can do is we can go ahead and solve the problem. So first, let's convert grams to moles. So we have the molar mass is given to us, so it's times 1 mole of ammonia over, and it looks like the molar mass is going to be 17.03 grams of ammonia. And so the next step is we got to convert moles of ammonia to liters of ammonia. And so let's think of some ratios we can write using this molar volume. We can write 1 mole of ammonia over 22.414 liters of ammonia, or we could write the reverse of that. So which one do we want to use to solve this problem? It looks like we want to use the reverse of this, right, to get an answer in liters of ammonia. So let me just give myself a little bit more room here. There we go. So it's times 22.414 liters of ammonia over 1 mole of ammonia. And so let's just confirm that the answer is going to be in the units that we want. So grams of ammonia cancels here, moles of ammonia cancels, and so we get an answer in liters of ammonia. And so I think if you work out the math and correct the answer to the right number of significant figures, it's going to be 9.74 liters of ammonia. So just to point out again that we can use this ratio of 22.414 liters of ammonia here to 1 mole of ammonia because we just happen to be at standard temperature and pressure. If the problem was dealing with other conditions of pressure and temperature, like say 2 atmospheres at 100 degrees Celsius, then we could not use that ratio to solve the problem. Okay, so let's move on to the next problem. Okay, so we have another problem here. So according to the reaction equation, and it looks like it's the reaction of formation of water from hydrogen and oxygen, if we have 2 liters of hydrogen react in excess of oxygen gas at standard temperature and pressure, how many grams of water are produced? Okay, so let me go ahead and write this equation out. So we have 2H2 plus O2 gives you 2H2O. And so we have 2 liters of hydrogen gas. And in the end, what we're trying to do is figure out how many grams of water are produced. So it's grams water. So there are actually 2 ways to solve this problem. I'm going to show you both ways. And so one way you can solve the problem is you can take the 2 liters of hydrogen, and because we are at standard temperature and pressure, we can convert this to moles of hydrogen using the molar volume of 22.414. And then once you're at moles hydrogen, you can convert that to moles water using the mole ratio. And then once you're at moles water, what you can do is convert this into grams water using the molar mass. So let me go ahead and write that out really quickly. So here we want to get this into moles of hydrogen. So it's 1 mole of hydrogen over the volume that this occupies at standard temperature and pressure, which is 22.414 liters of hydrogen, so that's fine. So now what we can do is, now we have moles hydrogen, we can convert this to moles of water using the ratio of 2 moles of hydrogen to 2 moles of water. So it's going to be 2 mole of water over 2 mole of hydrogen. And then what we can do is the final step is convert from moles water to grams water using the molar mass. So it'd be times 18.02 grams of water over 1 mole of water. And so I think if you worked this out, you would get the answer 1.61 grams. So let me show you a second way you can solve the problem. And so the second way would be this. You can start out with 2 liters of hydrogen again. But remember what I was telling you earlier is that these coefficients not only indicate a mole ratio, but because the molecules you are comparing here, hydrogen and water, are in the gaseous state, you can also think of this coefficients as being a volume ratio. And so you could choose the volumes to be units. So if you wanted to, you can take the 2 liters of hydrogen and using the ratio of 2 liters of hydrogen reacting with excess oxygen gives you 2 liters of water. You can figure out how many liters of water that would be. And then from the liters of water, using the molar volume because you're at STP to figure out the moles of water, and then moles of water using the molar mass to get the grams of water. So really quickly, it would be like this. It would be 2 liters of water over 2 liters of hydrogen. And again, the ratio here is 2 to 2. So again, these coefficients here not only apply to moles, but to volumes. Then what you have is you're going to have to get this into moles water. So 1 mole of water is equal to 22.414 liters of water because we are at standard temperature and pressure. And then the final step would be to multiply this by the molar mass of water. And so I think if you could do it this way and you should get exactly the same answer. So either way will be fine. Okay, so let's move on to a new concept here.